Good morning, friends. Welcome to the 11th standard. Today we are going to discuss about the last two chapters, oscillations and waves. These two chapters are most important for 12th standard because on the base of these two chapters we had to also study about the ray optics and wave optics in 12th standard in part 2. The weightage of this chapter is also more compared to the other chapter, right? And also, what are the equations for wave we discuss in chapter 15 and chapter 14? That is also most important for our study of 12th standard. And due to that reason, first we are going to discuss about the oscillation and also the wave, and also weightage of this chapter in 11th standard is also compared to the other chapter, that is the high weightage. Okay, first what is the in oscillation we are going to discuss about the periodic motion, and then oscillatory motion, and after that simple harmonic motion, and then we derive the equation of motion. Okay, for that purpose, first what is the motion? Already we discussed in chapter 3 for a particle. What is the particle? A point-like body having a mass that is known as a particle. The particle should possess the mass. Without the mass, in our physics, we not define this particle as a particle. Okay. If the body is very, very small in size, but it has the mass, so this body is known as the particle. How we say that the particle or the object is in motion? If and only if the position of this particle or this body changes with time or changes with respect to the other body or the other object. On a road, suppose the one bike is in motion. So the position of this bike is continuously changing with time. So we can say that this bike is in motion. If the position of this bike does not change with time or does not change with other object, so we say that this bike is in stationary position, not in motion. Clear this? Okay. Now, the different kind of the motion is the periodic motion and simple harmonic motion. In our daily life, we also see the other type of the motion, like as the motion of a pendulum of a wall clock. We know that the pendulum is oscillate like this way, or the motion of this pendulum is this. Actually, what's happened? This pendulum repeats its motion on a certain path about a definite point and also in definite interval of time. Definite interval of time. Okay. The second example is that the motion of the earth around the sun. Here the earth is moving on a circular path. Its motion is repeated at definite interval of time. Also, this motion is repeated on a certain path about a center. So that is also the example of periodic motion. So the definition of the periodic motion from this discussion is that if a body repeats its motion along a certain path about a fixed point in a definite interval of time. Here these 3 points are important. One is along a certain path. Second is about a fixed point. And third is in definite interval of time. A body repeats its motion along a certain path about a fixed point in a definite interval of time. Such motion is known as the periodic motion. Other example. Numbers of the example shown in our daily life. One bus daily start its journey from Anand bus stop, suppose at 8 a.m. to the Ahmedabad, which is at 10 a.m. Now 11 a.m. it starts its motion from Ahmedabad station to the Anand station, which is at 12 a.m. So this motion is also a periodic motion. The motion of this bus is repeated on a certain path about a fixed point and also in a definite interval of time. Such motion is known as periodic motion. Such motion is known as periodic motion. Again, the definition of periodic motion is that if a body repeats its motion along a certain path about a fixed point in a definite interval of time, such motion is known as the periodic motion. Now, the other examples given in our NCERT book, one is that an insect climbs up and down on a limb and repeats its motion. One insect moves up and down on a limb. So initially the insect is here, climb up, go to the certain point and again return back towards its initial position. Again going down, again moves up. So this insect repeats its motion on a certain path about a fixed point. Fixed point, that means its initial point in a definite interval of time. So such motion is also known as periodic motion. One insect again climbs up and down on a limb. So here, limb is the definite path. Initial position of the insect is known as the fixed point, and it repeats its motion at a definite interval of time. So such motion is the periodic motion. As we do the graph of such motion of an insect on a end, so the graph is this way. Here on the y-axis we consider the distance traveled by the insect and versus time. Initially at time t is equal to 0, that is at its initial point. Going to the maximum height, so this part, here it attains the maximum height. Then that is the come back or the return back up to the initial point. Again moves up, again return back. So here the motion is this way, like this way. So this is the repeated motion represented by the graph displacement or the distance versus time for a periodic motion. There is a graph for insect climbs up and down on a ramp and repeat its motion periodically. Now the second example of the periodic motion is if a child climbs up a step and comes down and repeats its motion. Like to this way, there is the steps. One child is at here. He step up, one step up, and then step down. So this type of the motion of a child, that is also a periodic motion. As we do the graph, so for certain time it is at initial position, then climb up, remain for the certain time and climb in down. Therefore climbs up and down, up and down. This type of the motion of the child is also a periodic motion. Clear? So there is the graph of the displacement above the ground versus time for a child, which step up and step down. And now the third example of periodic motion is that motion of a bouncing a ball between our palm and also the ground. Sometimes we are playing like to this way with a ball. There is the ground. We drop a ball towards the ground and ball is bounce and return back to a palm. That means we are bouncing a ball between the palm and the ground. So first we drop a ball in downward direction. So this ball is bouncing up. So this motion is also a periodic motion because this motion is repeated on a definite path about a fixed point ground and a definite interval of time. So there is also the example of periodic motion. S will be the graph of the height above the ground versus time for this ball. So here initially that is in our hand, that means in our palm, therefore some height from the ground. So initial position is this. Now there is the hit the ground at this point, that means after this time, and again return back to our palm. So this time is known as the periodic time or the time interval for one oscillation or the one complete motion. Again the process is repeated. Again the ball is hit the ground at this time and return back to our palm. So there is the graph of the height above the ground versus time for a bouncing ball between our palm and ground. That is also the example of periodic motion. We can add the equation of motion for this ball, and these equations are known as Newton's equation of motion. When the ball is moving up, so according to the equation of uniform accelerated motion, D is equal to V0t plus half at square. That already we did in chapter 3 and chapter 4. Here the ball is moving up, therefore the acceleration is gravitational acceleration, that is act in downward direction, therefore acceleration is negative, therefore height h or the displacement is v ut minus half gt square. U is the initial velocity, t is the time interval, minus half, g is the acceleration, and t is the time. When the ball is moving upward motion or during the upward motion from ground to the palm, at that time the equation of motion is represented by h is equal to ut minus half gt square for upward motion. And when the ball is hit the ground from the palm, at that time there is the downward motion, at that time the same equation, but here the direction of acceleration is changed, that is in opposite, therefore there is the positive. Therefore h is equal to ut plus half gt square for downward motion. So that is also the example of periodic motion. Now other example of periodic motion are shown in our daily life. One is the motion of a needle of sewing machine. In a sewing machine, here the needle is moves up and down. So here the motion of this needle between these 2 points, there is also repeated at definite interval of time. So that is the example of periodic motion. After that, the motion of piston of a railway engine. Now we also see the railway engine, actually the heat engine, not diesel or the electric engine. At that time the piston moves up and down at definite interval of time and also at a certain path. So there is this motion is also a periodic motion. There is the repeated motion on a certain path at definite interval of time. Now, revolution of a moon around the earth. There is the earth. Here, the moon is revolved around the earth on a circular path. Moon is repeated, or the going around the earth. So there is the circular motion. That is also the example of periodic motion. Here it is not necessary. On a certain path, that means the certain path is always linear. Any type of the path. Here the path for the ball is parabolic path. Now the motion of a needle of a sewing machine is the linear path. Now the evolution of a moon around the earth is circular path. But here the moon repeats its motion on a certain path about the earth at definite interval of time. Therefore, the motion of a moon around the earth is also the example of periodic motion. Now, motion of the wings of flying birds. When the bird is flying, so that its wings moves up and down periodically. So that is also the example of periodic motion. So there is the definition of periodic motion and also the different example of periodic motion. after the discussion of the periodic motion, we also discuss about the different type of the periodic motion and also its example. Now, what is the simplest or the simple definition of the periodic motion? The simple definition of periodic motion is that a motion that repeats itself at regular interval of time. A motion itself repeated at definite interval of time is known as the periodic motion. Again, the simple definition of periodic motion is that a motion that repeats itself at regular interval of time, that is the periodic motion. Now for periodic motion, no string force is produced. What is the string force? In case of a spring, as we pull or the push and we release, so what's happened? Whatever the displacement of the spring is take place during the pull of this spring, due to the properties of its elasticity, the string force is produced. This string force is brought back the spring to its original position. So here, this type of the string force is not produced. No string force is produced on a body. Henceforth, continuing this motion, the constant external force is required. Now, example is that as we hit the ball to the ground, for each and every oscillation, we have to apply the external force on a ball. Otherwise, what's happened? After the some oscillation, the motion is going to decreases. That means it last going to stop. Clear this? That means here the no string force is produced on a body. Henceforth, continuing such motion, external force is constantly required. So question arises in our mind that we also written in example. The rotation of the moon or the evolution of a moon around the earth, we apply the external force. So here we have written, in this type of the periodic motion, there is no restraining force are produced. For continuing this motion, external force is required. Now the moon is revolved around the earth. At the time, we apply the external force. The gravitational force or the gravitational force by the earth on the moon is responsible for this external force. Because the force of attraction by the earth on a moon will provide the necessary centripetal force. Necessary centripetal force. So this force acts as the external force to move the moon around the earth. All the periodic motion need not to be oscillatory motion. We are going to discuss in next portion about the oscillatory motion. At the time our concept about this sentence is going to clear. Now here keep in mind that all the periodic motion need not to be oscillatory motion. Some motion are the oscillatory, some are not. The motion of a pendulum wall clock, there is the periodic motion as well as there is the oscillatory motion. While the motion of the moon around the earth is periodic motion but not oscillatory motion. Okay. For example, the circular motion is periodic motion but it is not a oscillatory. Just we take the example of the moon revolve around the earth on a circular path. That is the periodic motion. This motion is repeated at the definite interval of time. But there is not a oscillatory motion. So keep in mind that the simplest or the simple definition of the periodic motion is that a motion that repeats itself at regular interval of time is known as the periodic motion. Now, keep in mind that for periodic motion, restraining force is not produced. Therefore, for continuing motion, the external force constantly required. Now, it is not necessary the periodic motion is to be oscillatory motion. Keep in mind this point because after the discussion of the periodic motion and oscillatory motion, for 2 marks question is that state the difference between periodic and oscillatory motion. At the time, at least 3 or 4 points of each and every motion we have to write down. Okay. After that, what is the oscillatory motion? Now the next question is that, what is the oscillatory motion? Give its example. Oscillatory motion is that if a body moves to and fro, back and forth, or up and down about a fixed point, in a definite interval of time, such motion is known as the oscillatory motion. That means, suppose the one body is here, initially at this point. So this body moves fro and to. Or in other words, if the body is, that is the equilibrium position or the mean position, moves up and down this way, a definite interval of time. So this motion is known as the oscillatory motion. Again, if a body moves to and fro, back and forth, or up and down about a fixed point in a definite interval of time, such motion is known as the oscillatory motion. Now here these words are important for this definition. If a body moves to and fro, back and forth, or up and down about a fixed point in a definite interval of time, such motion of a body is known as oscillatory motion. That means this body moves first from a point and to a point, again from a point to a point, about a fixed point. And this motion is repeated at definite interval of time. While the body is supposed at this point, moves up, then down, again moves up, a definite interval of time. Such motion is known as the oscillatory motion. Now the example of oscillatory motions are, first is, a ball placed in a bowl is in equilibrium at the bottom. So this type of the bowl, one ball is at bottom, there is an equilibrium position. Now we displace this ball from its equilibrium position in any one direction, like this way. We bring it here and we release. So what's happened? This ball is moving this way, again repeat its motion on this path, again moves in this way. Now a ball placed in a bowl is in equilibrium at the bottom. If displaced a little from the point, it will perform a oscillatory motion. There is a bowl. In this bowl, one ball is in equilibrium position at the bottom. Now we displace little from its equilibrium position and release. So this ball repeats its motion about the mean position to and fro, a definite interval of time. So this motion of the ball is known as the oscillatory motion. Now the next example of oscillatory motion is that the motion of the pendulum of a wall clock is also oscillatory motion. For that purpose, now here we take the example. Suppose there is the pendulum of a wall clock. There is an equilibrium position, x is equal to 0. Slightly we displace and release. So it performs the oscillation about the mean position, flow to. So this motion of a pendulum is known as the oscillatory motion. This direction, again this, again repeat it. Again, the motion of the pendulum of the wall clock is oscillatory motion. The pendulum is in equilibrium position at x is equal to 0. We slightly displaced and released. So the pendulum of the wall clock is oscillating about the mean position. So such motion of a pendulum is oscillatory motion. Now third example, the motion of a loaded spring. When the load attached to the spring is pull little from its mean position and release. So there is a rigid support. One spring is tied with rigid support, and at free end the load is suspended. So that is the equilibrium position y is equal to 0. That is the y is equal to 0. Now we pull down this body up to this point and we release. So it performs the oscillation in up and down direction. Initially, a spring is loaded, that means the load is attached at the free end of a spring. One end of a spring is tied with the rigid support. That is in equilibrium position. Now we slightly pull down and release. So this load is oscillate about their mean position. Y is equal to 0 up and down at definite interval of time. So the motion of this loaded or the load attached with the spring is known as the oscillatory motion. There is the third example of the oscillatory motion. Okay. So what's happened here? Yes, there is an equilibrium position, load. Yes, we pull down. So we apply the external force on this load in downward direction. So as a result, the restoring force is generated in upward direction. The restoring force F is equal to minus AY. This restoring force is directly proportional to the displacement and opposite to the displacement, direction of displacement. This restoring force produced in a spring due to elastic properties of a spring. So as we pull down and release, so due to this restoring force, this load is perform the oscillation about its mean position. Therefore, during oscillatory motion, the restoring force is produced, and such type of motion hence no required any external force. Initially, slightly external force is required, but during the continuing motion, we know apply any external force. While in periodic force, the external force continuously, constantly required for such type of the motion. But in oscillatory motion, no external force is required during the motion. Initially, that is required slightly displaced from its equilibrium position. Also, in a ball in a bowl, first we apply some force to displace from its equilibrium position. In case of a simple pendulum, pendulum is slightly displaced. Here we apply the external force, and also for a loaded spring, initially we apply some external force and then release. So it performs the oscillation about its mean position. So in a restoring force is produced in such type of the motion. Therefore, no external force is required. Now, every oscillatory motion is periodic motion, but every periodic motion need not be oscillatory. This sentence also we discuss in periodic motion. All periodic motion need not be oscillatory. May be oscillatory motion or may not be oscillatory motion. But all oscillatory motion are the periodic motion. Such type of the motion is also known as the harmonic motion, because here the motion is continuously moving between these 2 points, this and this. So here there is the y is equal to positive y, and here y is equal to minus y. Between these 2 points, it continuously performs the oscillation. Therefore, that is known as the harmonic motion. So there is the discussion about the oscillatory motion. Again, what is the definition? If a body moves to and fro, back and forth, or up and down about a fixed point in a definite interval of time, such motion is known as the oscillatory motion. Right? Second point is that during the oscillatory motion, the restoring force is produced, therefore no external force is required. Third point is every oscillatory motion are the periodic motion, but Every periodic motion need not be oscillatory. So these 3 points are important for the difference between the periodic motion and oscillatory motion.